Hello, this is Jack Jackson. In this section, we'll see how to use the built-in T-Test app on the TI calculators, the TI-84 and the TI-nspire, to do problems, do t-tests. Actually, a one-sample t-test. So we're actually going to do the same problem that I did in the previous video. So if you watch the one right before this, the video right before this in the playlist, you will see how we do this without the app, using a calculator for some calculations, but not the built-in shortcut app. In this one, this video, we're going to see how to use the built-in app. So just as we have seen z-interval, z-test, and t-interval apps built into the TI-84 and TI-nspire calculators, we similarly have a t-test app built into the calculators as well. We'll illustrate this with the problem from the previous video. So one sample Lefttailed Ttest detailed construction example. We did this before. We said the recommended amount of sleep for an adult human is 8 hours per night. So this previously worked example, we have this. So we've got the recommended amount of sleep for an adult human is 8 hours per night. However, a student life publication of a university indicates the average amount of sleep the college students living on its campus is 7 hours per night. We maybe suspect that that's still high. So we test this out. We make a random sample of college students where we survey them to see how many hours of sleep they got per night. The data collected is displayed below. We only selected a few of them to sample. We're going to test the hypothesis that the students actually get less than the reported 7 hours of sleep per night. We're going to use an alpha level of 0.1 or 10%. Now, first we might want to test to see if this is approximately normally distributed because we have a relatively low sample size. Let me count real fast. Just 10. So with just 10, we need it to be not highly non-normal at least. And we could do a normal probability plot. I actually showed that in the previous video if you want to see that. But that worked out okay. So we have what we need to run a t-test. Okay, so suppose we've checked everything to make sure we can run a t-test. The way we do this is we type our data into our calculator in the L1. If you just did this with the last video and you're now watching this one right away, it may still already be in there. Then we just go to our test, which is stat, with left arrow to test, and it's the second one, a t-test. Choose that, and then you'll go down to this screen down here. And our stuff is in data. We don't have the summary statistics. We actually have a data set. So we select data. The mu naught is the hypothesized mean. We assume that they're telling the truth, that they're accurate, that 7 is the hours per night on average. We tell it our data is in L1, frequency 1. We think it's less, so we're testing the hypothesis that got less. So that's a left or less than a left-tailed test. That's the one here in the middle. And then we could use calculate or draw. If we do calculate, we get this screen right here, which returns the alternative hypothesis, the t-star test statistic, the p-value, the x-bar value, the s-value, and the sample size. So the sample size is 10. The standard deviation of this sample is about 0.99666. The x-bar, or average amount of sleep for the people in this sample, is about 6.5 hours per night, with a p-value of 0.07355 and a test statistic t-star of negative 1.586. If we just had chosen draw instead, then the p-value is what is displayed on the t-distribution PDF. It gives us the value of that p-value, rounded off a little bit more than the other version gave us, but 0.0736, and a t-star test statistic, again rounded off a little bit more, but it's the same number. So we can look at this. If we'd like to see the visual, we can do that. If we just need the numbers, we can look at this screen. The only thing that this doesn't produce is the critical value, and that's not too hard to do. It's just an inverse t of the alpha with the degrees of freedom, which is n-1, and that we can produce that critical value if we need that. But mostly you really don't need that. You just really need what? That p-value. That's the key right there. So once we have that p-value, we can make our decision. And here's the same thing on the TI-nspire. We have our data in our a column here, which I called sleep. We run the test. So that's menu, statistics, stat test, number 2, t-test. It comes up with this dialog box first, choose data and OK. Enter in your hypothesized stuff, your hypothesis mean according to the null hypothesis is 7. Our list is called sleep, which is right here, frequency 1. Alternative hypothesis, you get your same 3 choices. This is a left-tailed, use the less than. Click OK. It returns this. And the main thing we need out of this is a p-value. It also gives back some other things, the degrees of freedom, the x-bar, the s, the n, the alternative hypothesis, the t-star test statistic, t, but most importantly, it returns that p-value. Again, the only thing it doesn't produce is the critical value, and you can do that by an inverse t here. Give it the alpha value and the sample size minus 1, which is the degrees of freedom. You put it the alpha value if it's a left-tailed test. So either way, what do we get? We got the test statistic is to the left of the critical value, and we got a p-value less than alpha. Either one of those things is enough to tell us that we reject the null hypothesis in favor of the alternative hypothesis. Note that you can use either the critical value or the p-value method with the same conclusion. However, in this particular case, the calculator directly produces the p-value, so the p-value is the easiest thing to use. So we state the conclusion and interpret it. Notice in our conclusion we include the sample mean, the hypothesized mean, the p-value, the alpha value, the type of test, and our conclusion stated in the context of the problem. We can usually do this in 1, 2, or 3 sentences. The mean amount of sleep for the students in the sample was 6.5 hours per night. This results in a p-value of 0.0735 from a one-sample left-tailed t-test. So at the alpha equals 0.1 level of significance, we see that there is sufficient evidence to conclude that the average amount of sleep for all students at this university is less than the hypothesized 7 hours of sleep per night. Our data indicates that their reporting of 7 hours per night in their article is incorrect, that in fact people are getting less sleep than that. Now notice that since we rejected the null hypothesis in favor of the alternative hypothesis, it's impossible for us to have made a type 2 error or type A correct conclusion. We had to have made one of the following: a type 1 error, well, we hope not, but this has happened if in fact the null hypothesis that the mean amount of sleep at all university students really is 7 hours per night, and we incorrectly rejected it. We were okay with having this happen with a probability of alpha equals 10%. If we only reject samples with the test statistic at or more extreme than the one we got, then we have made a type 1 error with only probability of p equals 0.0735, a little over 7%. A type B correct conclusion, we hope that's what really happened. This would be that we are correct in our conclusion that the mean amount of sleep by these students is less than 7 hours per night. We are 1 minus p, 93.65% confident that we made a correct conclusion. Here's another exercise for you to try. A machine fills cups with coffee. A sample of size 20 is taken, and we find that the average amount filled in this sample is 8.05 fluid ounces, and the sample standard deviation of the sample is 0.1 fluid ounces. A dot plot of the data suggests that the individuals are distributed fairly close to a normal distribution. The machine is supposed to distribute 8 fluid ounces of coffee. Assume that this is the mean distribution of the population. What is the probability that the average of the sample of 20 cups from this hypothesized population is actually more than 8.05 fluid ounces? Compute and illustrate. Well, we can use a shade T for this. And if we shade T, we give it from 8.05 minus 8 divided by 0.1 divided by square root of 20. That's, what is that? Well, that's the T-star test statistic. And I went up to 50 here. And then did a 19 degrees of freedom. That should at least be pretty close. And we graph that. It gives us an area that's pretty small, 0.01877. And we're doing a right-tailed thing here. So it's shaded here to the right. It's a little bit hard to even see any shading at all, but it's probably right in here. And the lower end of that is our test statistic, which was when you work all this stuff out here at the first thing. That's 2.23607, 19 degrees of freedom, and we went up to 50, which might as well be infinity in this case in terms of the numbers. So we get a very small area, very small probability there. What is a 90% confidence interval for the true mean of the coffee dispensed? Well, a 90% confidence interval for the true mean is about 8.01 to 8.09. We can get that from our t interval. Okay, and that t interval is given here. We'll do stat test t interval. Our data is statistics. We give it the x bar value, the s, the n is 20, confidence level, and calculate, and you get the t interval right there. Perform a test of hypothesis that the mean is greater than 8 fluid ounces. Well, what's the critical value and what's the test statistic? Well, if we want a critical value, we do inverse t of 0.95, 19 degrees of freedom, and there we get it. This is the test statistic that we just figured out a while ago. But in fact, we don't really need to figure out the test statistic that way because it's figured out by the calculator shortcut. So if we do the calculator shortcut, we can go to a t-test, stat, test, t-test, input our statistics. The mu naught is 8, hypothesized mean. The x bar value is a little bigger, 8.05. Standard deviation was given to be 0.1. N is 20. And we're doing a right-tailed test, so we choose this last one. We can do calculator draw. Draw gets us the bottom screen. Calculator gets this one. Either way, we get a p-value, 0.01877, 0.0188. Test statistic there. So either way, that computes the test statistic for us. And more importantly, it computes a p-value. So we look at either compare the test statistic to our inverse t that we did earlier to find our critical value. So compare test statistic to critical value, or I think better, compare the p-value to alpha. P is 0.0188. We fail to reject at the 0.01 level. If we'd chosen a different alpha, we don't have to do anything more calculations. If we'd say a 0.05 level, then we would have a strong enough P. It depends. So this area that you see shaded here on the drawing version is the P value. So the conclusion is performing a one-sample right-tailed t-test with a significance level of alpha equals 0.10 produced a p-value of 0.018. So there is enough evidence to conclude on average the machine distributes more than indicated 8 fluid ounces of coffee. And we're 90% confident that the true mean amount of coffee distributed by the machine is in the interval 8.01 to 8.09. So if we're using a 90% confidence interval, that's an alpha of 0.1, it's very good to give both the p-value and your t-test, but then also give the interval together. So that's very useful and very powerful to do. Had we used a different alpha value, we might have gotten a different conclusion, like alpha is 0.01. Conclusion would have been different. Okay, same problem. What's the probability? Suppose the true mean is actually 8.05 fluid ounces. What's the probability that a particular individual will get less than 8 ounces? What's the probability they'll get less than 7.9? Well, we could do those with normal CDFs, assuming that. So little variations there. The probability of getting less than 8 ounces is about 31%. and probably less than 7.9 ounces is less than 7%. You should be ready to do some homework problems on this, including problem 33 in the homework set, at least as they are set up as of me doing this video.